Friends, in the previous video, we have solved one of the problem with one of the end is on fixed and other end is on roller. Here, this one is another type of problem with one end is on fixed end and other is on roller with an intermediate support at B and the end support is C with an extended portion of C to D over a length of 2 meter and is subjected to 60 kilonewton at the free end. This one is single overhanged beam. Here A to B, it is subjected to 90 kilonewton load, point load at a distance of 2 meter and the total span is 2 plus 4, that is 6, with moment of inertia at 2I, and end support B is a roller B to C, that is 4 meter of span with moment of inertia I and is subjected to a UDL of 80 kilonewton per running meter. C to D is overhanged portion with moment of inertia I and the total length is 2 meter. First, we have to convert this overhanged portion into the moment. Here, the moment is 60 into 2, that is actual moment, that is in clockwise direction. M, C, D, that one is 60 into 2, that one is 120 kilonewton meter, that is actual moment of this force about C. Then first we have to find out the degree of freedom. You know that at A there is a fixed support. At fixed support the degree of freedom is 0, neither permitted to move nor permitted to rotate in any direction, hence the degree of freedom is 0 at A. At B, here it permits the rotation of the end of the beam on both sides of BA and BC. Then here there is no movement in the direction of the roller support since this end is fixed. Then theta B is the one of the degree of freedom at B. Similarly at C, here this is also roller. Here the degree of freedom theta C is the only one degree of freedom at end C, no lateral movement in the direction of the roller. Here the total degree of freedom is theta B, theta C, and this is 0, therefore it is 2. Hence we have to consider the theta B and theta C as the redundants. The fixed end moment. Here this span is subjected to MF EB equals, that is subjected to 90 kilonewton. Here A equals 2 meter, B equals 4 meter, that is minus WAB square by L square. By substituting the values, W is 90, A is 2, B is 4 divided by 6. That equals, by simplification, minus 80 kilonewton meter. Then from the other end, that is clockwise, that is WA square B by L square. W is 90, A is 2, B is 4 divided by L square, that is 6 square, that equals 40 kilonewton meter, that is clockwise, that is positive. Then for the next span BC, MFBC, that equals minus WL square by 12, that is subjected to a UDL of 80 kilonewton per running meter. ET into span is 4, WL square divided by 12, that one is minus 106.67 kilonewton meter. Similarly, MFCB, that is again 106.67 kilonewton meter from the other end. Here now we want to calculate the load due to the applied load at various coordinate points. Here this is coordinate 1, this is coordinate 2, that is P1 at coordinate 1 due to the applied loads in span AB and BC, that is 40 minus this one is 40, this one is minus, that is anticlockwise 106.67. Here the net moment at B or coordinate 1 is 66.67 with negative sign. Similarly, at coordinate 2 the applied load is 106.67 due to the fixed end moment, that is in clockwise direction, hence that is positive. Now we can write the stiffness matrix. We can write the stiffness matrix by applying the unit rotation at coordinate 1 and at coordinate 2 separately. First we can apply the unit rotation, that is theta b equals 1. Here, due to the application of the unit rotation at B at coordinate 1, here the displacement due to this unit rotation at B, here by converting the ends as fixed ends, then here it will undergo deformation. Here two spans are connected at coordinate 1, one is BA, one is BC. Then for the near end, for the both the spans BA and BC, 4 EI by L is the stiffness value. That is, by substituting for BA, that is 4 into moment of inertia is 2 times I, 2 EI. Then the flexural rigidity becomes 2 EI divided by L, that is 6. This is for span BA plus for span BC, that is for the near end, that is 4 EI by L is 4. Then the total stiffness value or stiffness element K11 equals 7 by 3 EI. Then due to this unit rotation, this is far end, that is K21, that 1 equals 2 EI by L in span CB or BC, that is 2 EI by 4, that 1 equals half EI. Now we can apply the unit load, unit displacement at coordinate 2, unit displacement at coordinate 2. Then due to the unit displacement at coordinate 2, now the displacement or deformation, due to this displacement, the deformation of the span BC, it will undergo deformation like this. Here the displacement theta c equals 1. Then this becomes the stiffness value at 2 due to the unit rotation applied at 2, that is K22. K22 becomes, that is near end for theta, then 4 EI by L. Then here EI is the flexural rigidity, L is the length, that is 4 meter, that is 1 over EI. Then K12, this becomes the far end, that is 2 EI by L, that is L is 4, hence EI by 2, that is K12 and K21. By observing the values, both are equal, that is by inverse reciprocal theorem, that is Maxwell's reciprocal theorem of deflection, we will get both the values are equal, that is K12 and K21. Now we can write the stiffness matrix K11. Here the elements of the stiffness matrix are K11, K12, K21, K22. Now by substituting the values, here K11 equals 7 by 3 EI, K12 that is 2 EI by 4, K21 that is 2 half of EI, then K22 that is 1 over EI, that is EI by 1. Then inverse of, now we want to calculate the inverse of this stiffness matrix, that is K inverse equals by getting the determinant value and by transposing of the matrix, column becomes rows and rows becomes column. Then you know how to calculate the inverse of the matrix. We know that the displacement matrix or displacement vector is given by inverse of the stiffness matrix into the vector of matrix vector due to the applied load minus the vector due to the loads if any. Then here we have theta b as the and theta c as the redundant. Then we have calculated the inverse of the stiffness matrix. The elements are 0.48 by ei. The elements are 1 minus half and 7 by 3 into the load due to any external loads. That is, we have converted this overhanged portion into the actual moment. That is, at 1 coordinate 1 at b no loads are applied, that is no pre-existing loads are applied, that is 0. But at 2 we have converted that overhang into actual moment. That is, actual moment is clockwise, in clockwise direction, that is 120 minus the load due to the moments, fixed end moments at coordinate 1 2. We have calculated the fixed end net fixed end moment at 1, that is minus 66.67, and at 2 that is 106.67. Here now minus into minus plus, this is 66.67, this one is 102 120 minus 106.67, that is 13.33. After simplification, you will get the values of the redundants theta b and theta c as 28.80 by ei. Then theta c equals minus 1.067 over ei. Then by using the values of the above displacement values in terms of ei, in terms of the flexural rigidity, now by using the slope deflection equations, we can calculate the final moments. Here MAB equals 2EI by L plus 2 times inside the bracket 2 times the near end slope plus 1 times the far end slope plus close the bracket plus MFAB. Here in span AB, the fixed end moment, that is at left end, MFAB is minus 80 in plus 2 into flexural rigidity is 2EI, hence 2 into 2 EI divided by L is 6. Inside the bracket 2 theta A is 0 since the original beam is and A is fixed, that hence theta A is 0. Theta B value we have calculated, that is 28.80 divided by EI. Here this EI get cancels. Then after simplification, MAB equals, that is minus 60.80 kilonewton meter, that is anti-clockwise. That one is anti-clockwise. Now MBA equals, again by using the slope deflection equation, 2EI by L inside of the bracket 2 times the near end plus 1 times the far end slope, that is plus MFBA, the fixed end moment at BA. Then the fixed end moment, that is plus 40, then 2 into flexural rigidity is 2EI by L is 6, inside of the bracket theta A is 0, 2 theta B, 2 into 28.80 by EI. After simplification, that is 78.40 kilonewton meter, that is clockwise. That one is clockwise. Then MBC, by using the slope deflection equation, 2EI by L inside of the bracket 2 times the near end theta B plus 1 times the far end theta C plus MFBC. Here MFBC is anti-clockwise, that is minus 106.67. Here the flexural rigidity is EI, 2 divided by 2 EI by length is 4 meter, inside of the bracket 2 theta B, 2 into theta B is 28.80 by EI minus theta C, that is minus 1.067 divided by EI. After simplification, here you will get 78 minus 78.40 kilonewton meter. That one is anti-clockwise. Then Here, by observing these two values, this one is 78.40 kilonewton meter. One is clockwise and one is anti-clockwise. This one is 60.80 kilonewton meter. Then next, MCB. MCB, that is again by the using the slope deflection equation 2ei by L, the near end that is 2 theta C plus 1 times far end theta B, in close the bracket, plus MFCB. MFCB is 106.67 plus 2ei by L is 4 into inside of the bracket 2 into theta C is minus 1.067 by EI plus 1 times theta B, that is 28.80 by EI. Then that is, after simplification, here you will get 120 kilonewton meter, that is clockwise. This one is clockwise. Then here you have calculated the actual moment. You have calculated the actual moment. Here in this overhang span, the resisting moment is 120 kilonewton meter, that we have to show. Then by using this, now we can draw the bending moment diagram. Here, by observing the above values, here first we have to draw the reference line or datum line. This one is the reference line. Here now this one is, here first we have to draw the reference line. This is the reference line. Then here at support A, the support moment is, that is 60.80, that is hogging. Now draw the ordinate of 60.80 kilonewton meter by considering a suitable scale at A. This is the ordinate. We can represent the hogging moment above the reference line and sagging sagging moment, that is span moments, that is support moments. Support moments, we can represent the hugging moment above the reference line and sagging moment below the reference line. Here at this point, here both the moments are support moments are hugging moments, hence draw the ordinate of 78.40. Then join these 2 points. Here we will get a trapezium. Then here by observing this 120 kilonewton meter, this 120 kilonewton meter, both are hugging moments, hence draw an ordinate of 120 kilonewton meter, that is above the reference line. Join these 2 points, then you will get again another trapezium. Then to draw the beam bending, simply supported beam bending moment diagram. To draw the simply supported beam bending moment diagram, now we can draw here from this end to this end. Here the bending moment is 0. At this point 60 into 1 is 60 into x 0 is 0. Then 60 into 2, that is hogging moment, hence the variation, that is it represents, that is mx equals w into x, that represent an equation of a straight line. The variation is a straight line. Then here in this span, simply supported beam bending moment, this is subjected to UDL. At support the bending moment is 0 and at the center the bending moment is maximum. The maximum bending moment is given by WL square by 8. That one is WL square by 8. Here that support the bending moment is 0. This one is a curve. This one is a parabolic or curvilinear like this. Then here by overlapping that bending moment diagram over the support moment diagram, here the shaded portion give us the net bending moment diagram. Here similarly, here this one is subjected to a point load. Here below the point load the bending moment is maximum. That one is WAB by L. That one is 90 into 2 into 4 divided by L. Here 90 into 2 into 4 divided by 6. that one is 120 kilonewton meter below the point load. Here at support the bending moment is 0. Here the shaded portion give us the net bending moment diagram. At support this is negative, at supports it is negative, and at the center that is positive bending moment as shown in figure. Now if we want to draw the shear force diagram, now you can calculate the support reactions. We can calculate the support reactions, that is summation of mb equals 0, summation of mb equals 0 by considering the LHS. That one is here Va into 6, that one is clockwise, that one is clockwise, minus support moment, that is 60.80, that is anti-clockwise, minus 90 into 4, that is also anti-clockwise, then plus that is 78.40, that is clockwise. Then Va equals, after simplification you will get Va equals 57.06 kilonewton, that is positive, that means that is upward. Then summation of mb equals 0 by considering the RHS of that one, that is here by taking the moments Vc equals 1 over 4 inside of the bracket 60 into 6, 60 into 6, that is the point load acting at the free end. Then due to UDL, that is 80 into the total span is 4 meter, which is acting at a distance of 2 meter either end, that is 80 into 4 into 2 minus the support moment, that is 78.40. Here you will get Vc equals 230.4 kilonewton. Then by applying another equilibrium equation, summation of V equals 0, here by taking the moments of all the four, by taking summation of the forces in vertical direction equals 0. Now Phoebe equals 90 plus 80 into 4 minus VA, that is 57.06, minus VC, that is 230.4, plus the force acting at the end point, that is at D, that is 60, then VB equals 182.55 kilonewton. Here now we can easily draw the shear force diagram for this one. Here from left, start from left, you know that left upward is positive. Here VA, that is 57.06, from this point to this point, here there is a point load of 90 kilonewton, that is 57.06 minus 90, that is downward, then you will get minus 32.94. Here from this point to this point, the shear force varies linearly, then minus 32.94 plus the, because of the support reaction VB, that one is 182.55, minus 32.94 plus 182.55, here you will get a shear force of plus 149.61. Due to the UDL in span B to C, that is 149.61 minus 80 into 4, that one is minus 170.4 kilonewton, minus 170.4 kilonewton. At C there is a support reaction of plus 230.4. Here you will get minus 170.4 plus 230.4. Here you will get a shear force of plus 60 kilonewton. Then it remains constant from C to D. At D there is a point load in downward direction, that is plus 60 minus 60, that becomes 0. Okay.